what is the total mass being accelerated now when I let go?
It's the same.
How much did you subtract, Tim?
Say it again.
How much did you subtract, Tim?
I moved 20 grams from here to there.
So it should be double
It should be this.
What should be doubled?
the acceleration.
Okay.
Wasn't that a thing in chapter?
Yeah, yes, the acceleration should double. But the question on the floor now is, what is the total mass being accelerated?
It's the same.
Yes, it is the same. Because if we're testing the relationship between force and acceleration, we want to keep mass constant. So all we did was move a mass from here to there to keep the total mass constant. And let's find out if we get roughly double the acceleration. Oh.
You need an assistant.
Should have gone old school and had you do it, this as your own lab. It's in. Cancel. All right. I think there was enough. I think it came off after the mass hit the ground, so I think we're good on that. So let's find out how close we got this time. Perfect. We got that nice parabolic curve again. And yeah, so you can see a little bit of a kink right there, which is showing up in the acceleration. So normally when you do a lab like this, one of the first things I ask you to do is clean the track. Because part of it, I think, is that the track's got grit or something in it. So position. Graph. Analyze. Curve fit. Position. Quadratic. Now, when you're doing the curve fit, one thing to notice is that you got the square brackets here and here. And I don't know if you can see them particularly well. Let's see if I can lighten that up a little bit. Don't know if that's any better. It feels like it was better there for a moment. There's a square bracket here, and that's what it's trying to curve fit against. It's trying to figure out what's the best curve that matches those points. Always should do a visual inspection to make sure it makes any sense whatsoever, because there, especially if you're doing sine curves, sometimes it just gets a little glitch and it just comes up with something just truly bizarre. But we now have 0.23667 as that coefficient, and so this is with the 0.196 newtons, and this would be 0.392 newtons. and our acceleration was 0.47.
334.
And our prediction was twice the acceleration. What happened?
We lessened the amount of force that's being pulled and increased the one that, and increased the mass of the force that's pulling, and therefore there was more acceleration on, more acceleration on a less amount of mass.
Now the total mass stayed the same.
But what part was pulling on what changed? So the mass of the little cart became less.
Would it,
The mass hanging did increase, but the total mass, because remember the total mass was what was hanging plus what's on the cart plus the cart itself.
Yes.
And all we did was move it from on the cart to hanging, but it still should have been in the total mass.
would it have doubled if nothing was removed from the cart, but you added another random?
The trouble with that is now suddenly we're adding additional mass to the problem. No, in theory, it should have doubled. But we are making an assumption here. Go to the force diagram. Or there's my force diagram right there. What assumption did we make about the cart?
That the normal force is equal?
And I think that's still pretty valid. If the cart was coming off the track slightly or digging into the track, then that would be an invalid assumption. I don't think that's the main assumption that's causing us problems here.
Is it the rope?
What about the rope?
It's not ideal. There's more.
Okay.
More
Friction.
tension.
That's a friction.
The mass of the rope itself we are ignoring. I don't think that's the major one, but somebody just say the
More
magic word.
tension. More tension.
Oh, no,
Friction.
that's the one, friction. We assume no friction is acting on the cart. Now it's possible I was first having issues when I first did use this cart, and then I noticed one of the wheels was a little bit off. So the question is that wheel now a little bit off again? All right, so here's a wheel that's not off. Here how long it's spinning. That one stops pretty quickly. This wheel's having issues. So that wheel is causing a drag. I thought I had it fixed, but apparently not. Well, as long as we're consistent on the friction, we should be able to still pull data off of this. However, I don't think we're getting consistent friction there. We got loads of time.
Could you stop the wheel so that it's just constantly stagnant and it just slides? If you have hot glue, you can glue it up so that it just stops.
That far. It's possible that if I take the bottom off of it, that might be an easy fix. Right, those are good. That's the bad one there. Yeah, there's. Let's run that first trial again and see if we get the same thing. If the wheel was working fine the first time, and then messed up, then that first trial is going to be the one that's off. And then we'll talk about how do you actually account for the friction without actually measuring the friction directly. All right, so let's try it. This is again the first trial, the one that we originally predicted to be 3-point-something meters per second squared. And now, and then we got 0.3 something. stop it abruptly before it gets that. All right. All right. We'll go through the same exercise again. This is, again, the first trial with the lane wheel. And we've been through the routine, so let's just highlight, analyze. All right, so I have a coefficient of 0.15311, so double that would be 0.30622. So it's still not too far off of what we did. 0.30622 meters per second squared. I guess that was simple enough to double in my head. All right, let's do another one, and then we'll eventually get around to seeing if this does match Newton's laws. We are noticing that it does accelerate the more force that's driving the whole thing. That should not be a shock. If you apply more force, it should accelerate more. So I'm going to have 50 grams hanging on the end over here. And so now we have a coefficient. You know what? It's a new trial. I'll show it to you. So I'm going to highlight, this is the point somewhere around here, and hit my finger and then skitter it on. So that looks like a decent part of the parabola. And matter of fact, let's graph. If you'll notice, up here it starts to curve the other direction. That's the point in which it basically was skidding to a stop. There's a little bit of a bump there. That could have been where my finger is. So why don't we start there, there, there. Analyze perfect position. Pretty decent parabolic fit. The black line there is exactly the equation that they did. So we have an A value of 0.39992. What's the acceleration?
0.79984.
79984 meters per second squared. And what did I have? I had 50 on the end? 50 grams?
Yes.
0.49 meters. And we'll do one more and then we'll shift gears.
Why do we double the A value?
Because the coefficient of the squared term is half of the acceleration. That's ultimately where it comes
Okay,
from.
okay.
I could go into the actual derivation of it, but I don't think it's the best use of time. But if you want to, afterwards, if you'd like to see it, I can do a quick derivation for you if you'd like. All right, and so now I'm going to move another 20 over here, so I'll have 70 grams total sitting on the end over here. As I pick up all the pieces. All right, so I got 70 grams down there. I still have a 10 grams sitting on the cart. And once again, just to let you know, this is the first time I've done sort of a group lab like this with this large of a group. So I'll be tweaking it next time. but thanks for your patience, well, as you were, I guess in some sense, guinea pigs at the moment. 2 experiments in 1. All right. And so we have an additional 20, so 0.686. This was 70 grams. Yep, got that. Okay, I was thinking there was a way to actually flip it upside down. All right, so I got the parabola right here. I'm gonna highlight the part where I feel confident it was going fine. I stopped it this time, so with my finger. Again, picking part of the parabola that is not at the ends. Analyze, curve fit, position, quadratic. And while it is rolling, that's a pretty decent fit right there. Now, in the labs that you did R squared value. On the flip side, R squared value tells you how good of a fit it is. This number at the bottom, the RMSE down here, that is the root mean square error that is related to R squared, but it tells you sort of the other side of it. This tells you how off it is as opposed to how good a fit it is. So you want the RMSE to be closer to 0, you want the R squared closer to 1. But we ended up with 0.565 as the A squared value, this part right here. And so our acceleration is whatever twice that is,
1.13.
1.13 meters per second squared. All right, so let's actually see how good this comes out. I don't need this anymore, at least not right now. Hey, we have 4 data points. I think a graph feels like it would be the perfect thing to do. So first off, in terms of the title, I'm comparing force and acceleration. Is it force times acceleration or acceleration times force?
Acceleration times force,
Why?
because it sounds right.
Because acceleration is dependent on force.
That's the reason, yes. It sounded right for a reason. Acceleration versus force. All right, so this is my acceleration axis here in meters per second squared, and this is my force axis here in newtons. Obviously, what I'm doing on the board here is a rather crude sketch, and we can do more precise over there. But at least let's get a crude sketch going. Now my force is going to range from just under 0.2 newtons to just under 0.7 newtons. So I'm going to do this, mark this off in terms of 0.1 newtons. So 0.1, 0.2. I probably should put the marks down first before I start numbering. Excuse my back. Roughly equal. So it's 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7. My acceleration goes from 0.3 up to 1.13. So I'm going to go in 0.2 increments. 0.2, 0.4, 0.6, 8, 1.0, 1.2. And now let's just hit some points. So at 0.196 newtons, we had 0.306, so somewhere around there. Spot on. And then at 0.392 newtons, so 392 puts us over here, and that was 0.47. And then 0.49, so just shy of 0.5, and an acceleration of just shy of 0.8. Looking pretty linear there. And then 0.686 and 1.1, somewhere around there. I would expect it to be in a straight line. Well, actually, let's talk about expectations. This is the equation right here that we're trying to figure out if it's true or not. I have acceleration on my vertical axis, so I need to actually put it in the other form, that acceleration is equal to force divided by mass. I've dropped the vector symbols for convenience. Since force is my variable here, I'm going to rewrite this as acceleration is equal to 1 over the mass times force. If you flash back to math class, they give you y equals mx plus b. I'm hoping that is familiar at least to enough of you. Actually, I'd like it to be familiar to all of you. Y equals mx plus b. I'm seeing enough nods around here. If you're not familiar with it, then this is the equation of a line. This is known as the slope-intercept form. The slope is the number in front of this variable, and that is the intercept. That's where it's going to cross the y-axis. So I take my equation and I try to put it in this form. Now, one of the issues that I have is that math people use m here. It actually comes from the French for mountain. Tom, with that? Anyone speak French?